Okay, hello everyone. This is going to be the first lecture I have on the little bits of fluid we're going to look at for the whole term. So I'm going to break these lectures up into smaller little chunks just because of the upload size. I'm having issue of having a whole big file. So for the rest of the class, I guess we're going to do it this way, where all of lecture 1 will be broken up into little things to watch. It'll be point 1, and then like this will be 01.1, and then I'll do another one that's kind of containing the ideas, or that would be 01.2, etc. So we'll go up to 01.k. So just a little note on why I have to do that, just because the files are too big. So if I'm trying to manageably get these out in a amount of time, I'm going to have to do this. So for watching all of lecture 1, you'll have to watch K videos. Okay, with that in mind, let's begin the idea of describing fluid mathematically, or in differential elements. So I already mentioned how what we're trying to describe is something like fluid in a pipe, or fluid in around some sort of object. So one fundamental thing that we'll have to at least have is a coordinate system. So for something like a pipe, we'll call this the x direction, or the axial direction of a pipe, and this will be the radial coordinate, right? So these are just good coordinate systems to have. For something like this, right, we can just use the good old Cartesian coordinate system, right, where we're just going to have, right, we'll call this x, and we'll call this y. Well, no matter what, even for something like this, if I zoom in to something really close to the surface right there, I'd still want to have some sort of coordinate system. So that's just one thing that we'll at least need, some way to measure or to assign numbers to things about fluids. Okay, so this allows us to write, we'll just write any old coordinate system. And I always use the term omega for my coordinate system. So for something like this, I have an x, a y, and a z. So now we'll just sort of write, the idea is I'm trying to describe some fluid. So I'll just make a little big undulating, right, some big undulating thing of fluid just sitting in space. So I'll have this be some volume of liquid, right? And this is just, right, some thing of fluid, right? In the same coordinate system, I can still have, right, I can still describe something like this, right, some sort of pipe. I'll just put it here, and then what happens is every point I could draw a vector to a point in that fluid. So that tells us that to really describe some sort of fluid, right, what are we doing? Well, we're taking this coordinate system that we've just made arbitrarily, and what I want to do is I want to be able to assign for every single point in this fluid, right? There's a bunch of them, right? A bunch of molecules of fluid. I'm trying to describe the velocity of that fluid moving around in space. So that means at every single little point in this space, I want to assign some vector, right? I want to assign some vector. So if you remember from Calc 4, what that object is then is a vector field, right? So we'll have V, right, some vector, and what's happening is it changes with time too. So this is already getting pretty complex, but you'll see where this is going. Right? Here's my blob. Right? Here's the volume of fluid. The volume of fluid is really a collection of x, y, z points in my coordinate system. So for every x, y, and z point that you give me, I will assign some vector to it, some vector describing the velocity of the fluid. And even worse, this is going to change with time. So this could move here at a different point of time, right? If this is at t equals 0, a little bit later, if this fluid was undulating around, it could just totally change. So now this point is now changed now to this point, and it's really, really complicated, but that's what we're describing. We're describing a whole vector field. You give me an x, y, z point and a value of time, I'm going to tell you a vector. And it's a field, so there's different vectors for every single point in your fluid. So that's the object we're going to use to describe fluid, right? And I think that I have this in the notes, right? For in terms of prescribing motion to something, we still are using Newton's second law. Newton's second law is the sum of the forces, right, is equal to mass times acceleration. These are little vectors that we'll have. But we have to address the fact that now this is not a point. This is now describing some vector field. And these now also have to describe some vector fields. So that's what this whole idea of a material derivative or substantial derivative too. That's what it's getting at. It's getting at a differential operator that still is okay with operating on these vector fields, these big blobs of fluid that at every single point give you a vector. Okay? So, right, let's just naively go about it like that. I know that acceleration is d v dt. Now we use a capital D for this material derivative. And you'll just see why, because it just behaves differently, right? But let's just say that acceleration is the time derivative of velocity, right? But remember that we know what velocity is. It gives you an x, a y, a z, and it needs a t to assign some sorts of vectors. So, right, this right, 4 arguments in this thing to take a derivative with. So we could just think of this as taking a regular derivative, but in terms of using the chain rule, right, you took Calc 4 to realize any multivariable function that assigns something, right, it's really the summation of little bits of change of each argument. So that means that this, right, some time rate of change with a vector, and then plus another additional change, which we're using the chain rule on, right? Because I'm taking everything in terms of time. So you see that these cancel out like you did in vector calc. And then we do it again. Okay, so we have these 4 terms, and all these are just they're just a linear, right? It's just taking each one of these, adding up the little changes, and doing chain rule on them. And that's the Calc 4 classic thing you learn out of a multivariable function. Is you want a small amount of change with respect to a quantity, you use this linear addition of changes. So the biggest thing that you learn when you do this, though, is these are pointwise velocities, right? So if I go to my blob of fluid, right, and I go to one point in there, add an x, y, and z point, I can project my coordinate system onto that very point, and then the point will be moving in space, and it has a u, a v, and a w. So, right, this point itself has some component, which is a x velocity, a y velocity, and a z velocity. That's exactly what these are. Right? So we just rewrite them like this. U, dx dt is a velocity, so that we call this one u. We call this one v. Call this one w. Right? And there's just, right, so this is the x component of velocity, the y component of velocity, and then the z component of velocity at a given point for every point in the fluid. And now this allows us just to make now a notation for what this differential operator really means. It's a shorthand. And I personally like a lot of the notations that come with these things because it doesn't take as long to write things out. So now we just define this thing, right, this operator, something like that. And we define it as a time derivative on a thing. And then on top of that, the vector field itself plus nabla operator, and then it will take an argument. So this operates as like, some people write like this and you have it in the notes, right? It's an operator, right? So it's waiting to accept something, and then it will do a differential operation onto it. So that's what the material derivative is, and I will in the next video describe some behaviors of it. But already off the bat, the thing is, what this material derivative allows us to do is just still write, right? Acceleration is a derivative of velocity. The only difference is really all that it's doing is this is now a vector field. This part is some special operator that operates on a vector field. So instead of a point or a vector, just one vector, which is what you did in physics too, this differential operator called the material derivative or substantial derivative extends it so it can operate on a whole vector field. Remember, my giant blob of fluid, right? I have to describe it as a vector field because every single point in there, in this volume of liquid, I need to describe some velocity, which is a vector. So that is the idea of this material derivative, which pops up a lot in the fluid differential analysis stuff. So I'm just motivating and letting you know where you're going to, right, when you see this capital DT thing, that's what it's describing. It's a different differential operator that describes accelerations in a fluid. And you get to it by just using chain rule, right, by just doing the chain rule and the linearization things that we learned in Calc 4. So it's a pretty simple calculation to do, but that's where it comes from. So I'm going to stop here, and then next I'll just do some implications of what this thing can do.